Hello everyone, hope you are doing well. I'm Reza, founder of the optimizationct.com. In this film, we are talking about the simplex methods for the transportation problem and how does it work. Let's move on.
So how we can solve this problem? Since the transportation problem is a specific instance of the linear programming, it can be solved using the simplex methods. However, due to the unique structure of the transportation problem we discussed earlier, a simpler approach can be utilized to obtain the optimal solution. Instead of employing the simplex table, the following table can be utilized to save the necessary information we use for solving the simplex method. So we can see that we have a box here. This is the uh, box for cost of transportation, and this is the box we mentioned here, the reduced cost. So whether a variable is basic or non-basic, we determine the information for the box as follows. Xij is a basic variable, the reduced cost is equal to 0, and the Xij is a non-basic variable. This is the reduced cost. So as you remember, if the variable is basic, the coefficient of that variable in the objective function is 0. So this is that 0, and this is the coefficient of the non-basic variable in the objective function in the row 0. So let's go to the algorithm. In the initial step, we aim to obtain a basic feasible region. In the transportation problem, there are various methods to generate the initial solution. Let's discuss one of these methods here. This is northwest corner rule. The northwest corner rule is a method used to generate the initial feasible solution for the transportation problem. It's based on a simple principle. Starting from the top left corner, northwest corner of the northwest corner of the transportation matrix, we allocate shipment in the greedy manner. So this is the step here. First, we begin the top left cell of the transportation matrix. Allocate. In the second part, allocate the maximum possible amount of unit from the current cell to the corresponding supply and the demand allocation. In third step, move to the next cell to the right if the supply in the current row is exhausted, or move down if the demand in the current column is fulfilled. In the fourth step, repeat steps 2 and 3 until the all supply and demand are satisfied. This process continues until the all supply and demand value are used, resulting in an initial feasible solution for the transportation problem. So, what happened in this rule? We first select the variable x11 here as a basic variable. Then following this rule, the northwest corner rule, if xij is a current basic variable and the demand from source I is not exhausted, we choose the variable x here, xij plus 1 as a basic variable for the next iteration. However, if the supply from source I is fulfilled, we select xi plus 1j as a basic variable. For instance, consider the simplex table below here for finding the initial basic feasible solution for the northwest corner rule. We start from x11. The maximum value is 30. For 30 and 50, we have the maximum value for improving this initial solution. We modify these two values because the demand is fulfilled here. So we go to the right. We go to the x12. The maximum value is 20 here, and we modify these two values. 20 is to 0 and 20 here is to 0. Because demand and supply are both exhausted, we can move right or down. We move down here. and we continue till we satisfy all demand and destination. So this is the initial basic solution with the corner west rule, with the northwest corner rule. So this is the basic initial solution. We start for the algorithm using the simplex methods. The previous method we discussed does not consider the cost, which means it may not result in a solution with the lowest total cost. To address this, the Vogel approximation method is introduced. This method is quite effective and is sometimes used to obtain and approximate optimal solution. Now, how Vogel's approximation work? In the first step, we calculate the difference between the smallest and the second smallest cost for each row and the column that is not yet fully allocated. In the second step, identify the row and the column with the largest difference. In the third step, we select the variable that has the lowest unit cost among those variables in the row or column defined in step 2. In step 4, allocate as many units as possible using the variable, consider supply and demand constraint. And in step 5, we repeat step 1 to 4 until all supply and demand are satisfied. By applying the Vogel approximation method, we can obtain an initial basic solution for the given simplex method while considering the cost. So this is the table we use to find the initial basic solution for the Vogel approximation methods. This is the difference in this column and in this here. You can find the difference between the minimum cost and the second minimum cost. So this is the minimum cost and this is the second minimum cost. We pick the maximum value, this is the maximum value, and choose the cell with the minimum value of cost. So this is the 0 is equal, it is the minimum value. And the minimum value of the demand and the supply here is 13. So we update 13 to 0, 50 is equal to 20, and we remove the column 4, and we have the x44 is equal to 30. And go to the next iteration. In the next iteration, you can see that we don't have the row 4. So we calculate the difference between the minimum cost and second minimum cost. We pick the maximum value and choose the cell with the minimum value here, and we find the minimum value of the 20 and 16 is equal to 20. So it means we remove in the next iteration row number 4 and update 20 to 0, and 6 is equal to 14. And we continue this process until the demand and the supply are satisfied. So this is the initial basic solution for the transportation problem with the help of the Vogel approximation methods. So let's back to the simplex methods for the transportation problem. Now we have the initial solution. In the next step, we are talking about the stopping condition. The purpose of the stopping condition is to determine whether the current feasible solution is optimal or not. A feasible basic solution is considered optimal if and only if the following condition holds true for all non-basic variables. So if the Cij minus Ui minus Vj is non-negative, we have the optimal solution. To assess these conditions, the value of the Ui and Yj should be calculated. If the variable Xij is a basic, then Cij is equal to Ui plus Vj. We can calculate the Ui and Vj by solving the equation associated with the basic variable. because the number of variable is one more than the number of equation is very important point. Finding the solution requires setting a one variable to a desired value, for example 0, and obtain the value of the other variable. So to illustrate this, let's consider the basic variable here x3 1, x3 2, x3 4, x2 1, x2 3, x1 3, x1 5, and x4 5. In this case, we have the following equation because these variables are basic. To simplify the explanation, let's assume the u3 is equal to 0, as it appears more frequently in the equation. By doing so, we can determine the value of the remaining variable as follows. So v1, v2, v3, v4, u1, u2, u3 here. So we can calculate u1, u2, u3, u4, and v1, v2, v3, v4, and v5. So this is the optimal value of the dual variable. During the deduce step, we determine the input basic variable and the output basic variable. In the simplex method for the transportation problem, we choose the variable with the smallest negative value of the Cij minus ui minus vj as the input basic variable. Taking into account this variable by the simplex table as follows. So the red box is the reduce box for the non-basic variable. If the all value are non-negative, the optimal solution is found. In the given table, the variable x25 has the smallest value of Cij minus ui minus vj and is chosen as the input variable because it is negative. To determine the basic output variable from the base, we employ the following method. We use the cyclist process to update the flow of the arc. If we add the value, if we add the arc with the flow of the theta, we update the other variable as a follow. In this figure, the value of the theta need to be increased to ensure that the cost of the all arc, the flow of the R arc is non-negative. By increasing the value of the theta by 10, we remove the variable x15 from the basic variable, making it the output basic variable. As a result, the updated basic variable is as follows. So if we set the theta is equal to 0, is equal to 10, we have this is the new basic variable. And we continue the process. Before we proceed with the solving the example using the simplex method for transportation problem, let's continue with the formal explanation of the simplex method for the transportation problem. In the initial step, we obtain the initial basic solution using either the northeast corner rule or Vogel approximation method. In the stopping condition, we solve the equation Cij is equal to ui plus vj for the basic variable to determine the value of the ui and vj. If the conditions Cij minus ui minus vj is non-negative hold for all non-basic variable, the current basic solution is optimal. Otherwise, we proceed to the iterative step. We have the three parts in the iterative step. Identify the non-basic variable xij that has the most negative value of the Cij minus ui minus vj as the input basic variable. Determine the output basic variable as a cyclic process. And then calculate the new basic variable. Go back to the stopping condition and repeat the process till the stopping condition satisfied. Thank you so much for watching me. If you are any question and need any assistance, please do not hesitate to contact us by email or by filling the contact form in our website, which is www.optimizationcity.com. Thank you so much and goodbye for now.